Hello everybody, my name is Iftikhar Ahmed and you're watching my channel Physics by Iftikhar. So today we are going to study about Lloyd's mirror experiment. This is the one of the method by which we can get the interference pattern. We get the interference pattern because we want to study how light behaves. So different scientists gave different ideas and different techniques to get the interference pattern. Okay, so similarly the Lloyd gave one of the beautiful and a genius method, and yet a simple method by which we can get the interference pattern. Okay, so we'll start. So Lloyd's used a mirror, a single mirror. The length of this mirror is approximately 30 centimeter, and the width of it is it can be 6 to 8 centimeters. So he used this mirror, and the specialty of this mirror is the top surface of this mirror is completely polished. Okay, polished because we want to get reflection from the top surface. That's why this mirror is completely silvered. Okay, silvered polish. And the bottom of it, the bottom of the mirror, what he did, he blackened the bottom surface of the mirror to avoid the multiple reflection. So when the light hits the bottom, it should not come out from it. If the black surface will be there, and that black surface will absorb that light, and that light won't disturb the interfering light again. So that's why the bottom layer of it is completely blackened, so that we can avoid the multiple reflection. Okay, this was the mirror. So here's the mirror. Now in the Lloyd's mirror we have to use a source S1. I'm using a source S1. So from this source I'll be getting light rays in this direction. So this is the interference this is the method in which we get the interference due to division of wavefronts. So here initially we'll be having a whole wavefront. So the wavefront is coming in this direction. So all the light rays which are falling on the top surface of the mirror, Lloyd's mirror, they will get reflect, and they won't be traveling in the same direction because of the angle, the reflected rays will travel something like this. These are the reflected light rays, and the rays from here, they will travel straight. So here's my final screen. On this final screen, I will observe the interference pattern only at some specific place. Not all the screen is having the interference pattern. Why? Because we know that to have the interference pattern, the coherence should be there. So actually by using this mirror, we have created a source, an imaginary source. This is that source. So this is that imaginary source which we have created by using the Lloyd's mirror, Lloyd's single mirror. So this mirror will give light as if there is some source producing light. So because this light is having same wavelength as that of this light, because they are coming from the same source, that's why the condition of coherence got satisfied, and the wavefront from here and the wavefront, let me explain like this, you see, yeah, wait a minute, the whole wavefront was coming like this, the part of it got reflected from here, and because of that reflection it got changed its angle. So now you have the other wavefront, and this one was the initial wavefront. So they are meeting at some point on the final screen, because these waves are from the same source and they have the same frequency, same wavelength, and they both satisfy the coherent condition, and that's why in this particular region here you will get interference fringes. Not in this region, you will not get any kind of fringes in this particular region. Why? Because this region is illuminated by a single wavefront. You see the wavefront from this light directly, they are coming from here, from S1, they are coming here, and there is no any kind of interference, any kind of interference from these light sources. That's why you won't see any interference in here. Why you are seeing in this particular region? Because the light from this source and the light from the light from S1, they are merging, and that's why you are seeing the interference only in this particular region. That's the thing. Now this point, the final screen, so here's the, wait, so what we know from the previous classes and previous experiments, what we used to observe and what we predict according to the previous experiments, we predict that if you are getting the interference pattern, the place which is exactly the bisector between, you see this distance, exactly the middle of it, this point on the final screen, we used to get the central maxima in the previous experiments. But you see in this particular experiment, we are not getting any central maxima at point A. Okay, not even maxima, we are not even getting any interference pattern there. Forget about the maxima. We are not even getting the interference pattern. If suppose you want to get the interference pattern at this particular point O, what you should have to do is, if you shift the final screen towards the mirror, you will get a point where you can have the central maxima, you can have the fringe at point O. It would be something like this. If I shift the final screen near to the mirror, so this is the point where you can have the fringes at center. Also you can have the fringes. Why? Because here this light rays are there, and the light rays from S is also there. The light rays from the reflected light rays and the light rays from S, both are there in this particular region. That's why you can have the interference pattern at O. Okay, and the other thing is that initially we used to see that, and we know that at point A we will get a bright fringe. Okay, but in this experiment there's something different is happening. We are not getting the bright fringe as the central fringe. Instead of the bright fringe, we are getting a dark fringe. Why? So let's solve this mystery. Why we are getting the dark fringe at the center? So for that purpose, we need to have the bit basic, like we should. I think you all are familiar when the light will hit a surface, and if it is traveling from a rarer medium to denser medium, when the light hit the surface and get reflected back from the surface, the reflected light will have the phase difference pi and the path difference lambda by 2. I hope you know this. So because the light ray, the reflected light rays are having the phase difference of pi and the path difference of lambda by 2, because of this path difference, the condition of destructive interference got satisfied at the point O, and that's why you are getting the dark fringe as the central. The zeroth order fringe is no more the bright one. It is now, in this experiment, it is a dark fringe. Because of the reflection from this mirror, the light will suffer the phase difference and path difference of lambda by 2. Are you getting my point? That is why. Now we know from the other experiments, Lloyd's, the Fresnel biprism and the Young's double slit experiment, the fringe width beta. We have the expression for the fringe width beta. So now we'll study how to find out the wavelength of unknown source by using the Lloyd's mirror experiments. So the light source whose wavelength you want to find out, put that light source here. So there will be a slit here, always there will be a slit. Whenever I'm saying there is a source, this is not the direct light source. Actually that light is you're passing through a thin fine slit, and from that slit the light is coming. Always remember, whenever I say the source, that represents the slit, not the main source. That is not the main source. Now put that source in here, and we know a formula for the fringe width beta. So what we are doing, determination of lambda. Okay, so we know fringe width beta is equals to lambda L by D. So with this expression we can find out the wavelength of unknown source. That is, lambda is equals to beta D by, am I doing it right? Yeah, by L. Okay, so this is the formula by which you can find out the wavelength of unknown source. For that, what you need to know, the beta fringe width. How will you find out the fringe width beta? Simple, using the movable microscope. So there will be, in the experimental setup, there will be a movable microscope and there will be a crosswire on it. I've discussed how to find out the fringe width beta in the Fresnel biprism experiment. Same like that, you have to find out beta fringe width here also. And the D, we know the distance from the source S1 and S2, and L is the distance from S1, S2 to the final screen. This is how you can find out the wavelength of unknown source by using Fresnel biprism experiment. No, not Fresnel biprism, by using Lloyd's mirror experiment. Thank you so much. That's it for today.